John here, wrapping up the Sprite state machine stuff. We left off last time looking at this is the end of the always block that we talked about last time that scans the sprite attribute table. Let's talk about the sprites themselves and look at the timing. Big thanks to everybody that supports my channel, list likers, subscribers, and all my Patreons, especially the VIPs listed here. Thank you very much. All right, so what's down here that we didn't get to? Here's a priority encoder where we output the color of the stack of sprites that we're going to render. And remember that 0 is transparent and that the parent module to this one deals with that transparency accordingly by showing that which comes out of the tiled graphics logic if there's not a sprite pixel obscuring it, right? Well, this is the same exact logic here, but we have at most 4 sprites that we can render on a given line, and those are providing as output these sprite color out in this array here. These are array of each element is a 4-bit vector. And if it's not 0, we know that it is an opaque pixel color coming from this sprite, which is the highest priority sprite, the first one encountered when we scan in order. I talked about that last time. So if the highest priority sprite that we found while scanning is opaque, we're going to send that color out. Otherwise, the next priority and so on, down to the 4th one that we found while scanning. Now, nowhere in here do we actually ask if the sprite exists in any way, shape, or form. And that I mean, what if it didn't find any while scanning? Are we going to send out these colors? Well, remember I said earlier that when we reset the sprite objects, they become transparent. So we can just process them anyway. It simplifies the circuit and the logic. So all 4 of these would be transparent if the sprite attribute scanning turned up no sprites at all. Okay? What else is going on? The rest of this you've seen before. This is the technique that I use for assigning values to module output ports, including this color out right here. And the reason I do this, if you haven't picked it up yet, is because while you're editing, editing your code, you're testing, and you want to do a quick hack and change something, it's really convenient to come down here and just change these values in some way so that this module can output some other function, especially while you're simulating and whatnot. The alternative is to go and change the value you're assigning to these regs, which happens in this state machine up here, which, as you may recall, is a little more visually noisy. Gets a little busy in here. And if you're modifying it and you want to put it back, it's a mess. Down here, much more convenient. So what is the module going to output? Definitively, it comes from here. And this is where we can put this priority encoder, right? Okay, so what have we not really covered yet? We haven't covered this module here, the sprite module. As I mentioned last time, we create 4 of these, one for each of the 4 sprites that are allowed to be visible on the current line. And we connect them up as I described in the last video. Remember the special reset stuff. This thing here is used to continuously reset the sprite before we load the various program parameters into them from the SAT and the configuration register. This here comes from the VGA sync generator and represents the last column on a given row, which is really the column before the left border on the current row. And we talked about that before when we were dealing with the graphics state machine for the tiled main active region of the screen. This is probably not the best name. Someday I'll go through perhaps and clean up a few things. So yeah, when we get on the other side of looking at the definition of this thing, yeah, maybe I could have called that something a little bit better. But the bottom line is that column 0 in this particular context is column 0 of the whole screen, not the active display. In other words, this tick goes active one VGA pixel period before we start rendering the left border. Okay. The rest of these come from the sprite attribute table. The load tick comes from the state machine we talked about last time that says this is the time that all the values in these variables are valid, and you want to program it into the chosen sprite. And this is the output of the sprite that we just saw below that feeds into our priority encoder and out of this particular module. Okay? Let's look now at the sprite itself. Turns out this is relatively simple because the state machine is where all the real action is. What have we got here? One of these sprites. So I'll remind myself to mention these few tidbits right here. Number one, as we saw before, all the patterns by the time they get loaded into this sprite module will always be 16 bits wide. 16 pixels wide. 16 VDP pixels wide, I should say. And that if we have an 8-bit sprite, which is obviously one of the modes, right? If it's not, if sprite size is not true, then it's an 8-bit wide sprite. And in that case, the least significant byte of the pattern on this input port right there will always be set to 0. In other words, it'll be transparent. So as far as this sprite is concerned down here, all sprites always have a pattern that is 16 pixels wide. The size parameter is not handled here. As I said, that happens in the state machine that generates this pattern to send down here. 1 VDP pixel, remember, equals 2 pix clock periods. Again, this probably should have been called VGA clock. I'm sorry. Again, something to rename maybe in the second pass of this thing someday. Note that mag can double the size to 32 by 32 max. So we talked about magnification last time as well. So mag is handled in here, as we'll see below. But the size is dealt with in the state machine that decides whether this is going to have 16 bits of pattern in it or only 8, followed by transparent kind of pattern in here, okay? Foreground color comes directly out of the sprite attribute table. The HPOS, notice we have a 9-bit value here. The value that comes out of the sprite attribute has 8 bits in it. This is 9, and what we have here is that 0 means the far left edge. I should probably add some more comments in here. Far left edge of the screen itself. In other words, 0 represents the far left edge of the left border, not the far left edge of the active region. So if there's a border, mapping out a window here for the active region, the column 0 is in the active region in a lot of the contexts in which you think of the VDP. But this 0 is the far left of the entire physical frame. Okay? So the point is the whole early clock foolishness is all gone by the time it gets to this thing. And HPOS is the absolute pixel number in VDP pixel units from the farthest left visible pixel on the screen, not the active display, all right? Load tick, as I said before, goes true for 1 tick period when the sprite object should capture the current value of all these things. Here, color out is the output color that we're going to get from the sprite. And the usual state machine, bunch of registers and the next values. We copy over the next to the current register value, every positive edge of pix clock. So this runs, remember, in VGA pixel units. And then our state machine is a whole down here. And a quick scroll through it, that's the whole thing. All right, so this isn't too bad. All right, so what do we got? We have, in almost all cases, the next value of every one of the state registers just stays frozen unless we override it down below. This is the only one that's not, and this is like really poorly named, so I just added this comment over here to remind myself that this actually counts VGA pixels in spite of this name. I probably redesigned, in fact, in my mind, I'm remembering I did. This thing has evolved a little bit during the debugging process. Some poorly named variables in here, I say. All right, so what this thing does, it counts continuously up by 1 for every VGA pixel as we go across the screen. This thing gets reset to 0 down here when there's a col 0 tick, which represents the beginning, as I just described, of the scan line, the pixel before the first pixel on the left border, okay? So this thing is really our column counter of VGA pixels across the screen. But the origin of it is the far left edge of the border. This, in theory, might be able to be derived from signals coming out of the VGA sync module, but this thing, like I said, evolved through much editing and hacking to get to its current state. This may be redundant, is my point. And in theory, if it is literally redundant, then the compiler should actually optimize this out. At some point, maybe what we'll do in a different video is go look at some of the things that we can find that the compiler really helps us with, and maybe things that the compiler can get fooled by and not so much help us with. All right? So what do we got here? Load tick. So yeah, when load tick is true, that means, like I said before, we're going to set all these variable values to the configuration inputs on our module. So you get the mag, hpos, and stuff like the pattern, the color, right? This thing here, what does that mean? And the active next, what do these things mean? First of all, the active next is the easier to understand, and that is that this thing becomes 1, as you can see right here, when we get the col 0 tick signal from the VGA sync module. And the reason it is in there is it lets us know, we'll see down below, when we're supposed to be rendering VGA sprite pattern pixels out of our output, okay? And we'll see that what happens is as soon as ActiveNext becomes true, we're either outputting transparent pixels or the sprite color pixels as we go across the screen. Now, this one down here has to do with remembering whether we are supposed to start on an even or an odd column. Well, obviously, whenever hpos 0 is true, remember this is the already EC compensated horizontal position where the pixel's supposed to start rendering expressed in VDP pixel units, all right? If that's a 1, it's an odd number. If it's 0, it's even. And the significance of this has to do with magnified sprites. I'll leave it as a test to the viewer to play around with this and see what happens if you either don't set it or set it wrong and stuff like that. We'll see down here what really happens, but this is kind of subtle, all right? Okay, so what happens? If it's active, and active happens as a result of the col 0. So this thing is stalled when it's configured, all right? What happens is when it's configured, ActiveNext is 0. We set all these values, and because ActiveNext is 0, which gets put into ActiveReg, in the above, always up here in the usual way, right? Whenever ActiveReg is 0, this whole thing down here will not be executed. It's seized in my mind. It won't go, okay? It starts running when ActiveNext becomes true. When we finally get to the part of the screen we're going to actually see. We also want to ask if that thing is what? Set to true. What's happening here is we're dividing the VGA clock by 2 by doing this. I think I discussed this when we talked about the graphics state machine earlier. All right, so it's so that every other clock tick, we don't bother going through here because we need to double all the VGA pixels in order to come up with one VDP pixel. So whenever we're about ready to update a VDP pixel, this thing will go and execute. So what do? We ask, does the horizontal position register equal 0 or not? Well, if it's not 0, what are we doing? What we're doing in that time is we're waiting for the pixel count to get to the point where we want to see our sprite. because we start, as I said before, 0 on the left, and the pixel numbers count up as we go to the right. So at the beginning of the load, we store our HPOS value from the sat table scan logic we talked about last time to some value. And what we're going to do if it's not 0, and we're rendering actual pixels, we start counting down. So if it's supposed to start at column 20, and HPOS starts at 20, every time we see a pixel, it goes down by 1, 19, 18, 17, and so on. When it gets down to 0, that's when we're supposed to see this sprite. So when it gets down to 0, this thing becomes 0. This thing goes false and stays false forever because nobody else is going to modify this until the next load tick. Okay? And therefore, we go to the else, which is the part of the screen, I like to think in terms of time here, where we can see sprite pixels. And we stay here until the next time we get a load tick. So what are we doing in here? The easy case is when we're not magnifying the sprite. Well, at this point, we should look at this first. Okay? This only makes sense if you know what we're doing with these bits, because this is obviously shifting to the left here, right? Well, how does the output use this pattern is the next question, right? Well, let's just put a pin on this for 10 seconds here and come down here and have a look-see. What do we do? Our color that comes out of this module for this sprite, as it says, sprite is showing when active reg is true. You know, we're in harm's way. We're rendering pixels on the screen when active reg is true. That happens up right here, right? So, and if HPOS reg is 0, as I just explained, we're in the part of the screen that's not only just, active in terms of the sprite. Don't confuse that with the active display region. Again, perhaps a bad named variable here. That is a sprite active, which starts far physical left edge, not, inside the border. So when that's true and HPOS is 0, we know we have already moved to the part where the sprite could be visible, right? So if it's, set to whatever, let's say, about halfway across the screen would be around 128 VDP pixels because it's 256 total. And if the sprite line we're rendering is supposed to be, this streak of on like that. So it'll be roughly, halfway across the screen then, right? So it'll have become 0 because it counts down for each VDP pixel. Once it becomes 0, the high order bit of the pattern, which is what we're looking down here right now, if that is also true, 1, it's supposed to be opaque when that's the case, right? Then we send out the foreground color that we got from the sat table. Otherwise, we're rendering a sprite, but it's not an opaque pixel yet. It's 0, okay? So that's how this works. In other words, the short of it is that the most significant bit of the pattern reg in our state machine here represents whether or not we're painting an opaque pixel or not. And that's only useful and valid when we've gotten to the point where the sprite should be seen on the screen that's being rendered, okay? Otherwise, we're transparent. And as you saw before, if it's transparent, anytime it's transparent, it's perfectly fine, and we output transparent as a whole from the above state machine, provided, I guess, I should remind you that all 4 stacked up, potentially stacked up, sprites have to all be transparent for that to be the case, where, then no sprites are visible. Okay, so back to here. What does it mean? Well, if we're not magnifying, then the pattern is shifted to the left 1 pixel on every single VDP clock, remember, which is when that's true. But if we magnify it, what we want to do is we want to change our shifting so that it only shifts every other VDP pixel clock period. Because what we've done is smeared 1 pattern pixel bit across 2 horizontal VDP bits. Okay? Now, this is where this phase jazz comes into play. You may have to pause this, draw yourself a little picture, think about it for a minute. But the short of it is, we can magnify the horizontal width of a sprite, but we're not magnifying the HPOS value. So if you have a giganto sprite that starts at column 100, approximately right there, if this was the VDP screen, right? Then it would also start visibly in the same spot if it was not big. Magnified or not, the first pixel of the sprite that could be opaque would be approximately right there. So we need to count down our HPOS no matter what, and we need to start rendering our pixels when HPOS gets to 0. But then the question becomes, how do we know to shift left? We need to shift left every other time we come through this loop. And the problem is, if you start in an odd column and you use something simplistic, like if if this thing is a 1, remember this is actually the VGA pixel column counter, and bit number 1 is counting up and changing its value once for every VDP pixel, and that divides it by 2, right? Because VGA has twice the pixels of VDP, and when mag is on, even the VDP has to divide it by 2 as well. Now, if you just wanted to shift every other pixel, you could say if this thing is true on its own and ignore this. That would certainly cause this to shift every other pixel. But we need to make sure that when we do shift left, we have just completed rendering 2 VDP pixels with the current pattern. So if we start in an, let's say we start in an even column, right? Then the column number would end in 0. This thing here would be 0. Okay? And again, this is your VDP column number. So if that is 0, and we just finished rendering column 0, then we render column 1, that would be 2 units that would represent 1 pixel on the horizontal axis of the sprite pattern that we want to put on the screen. And that is when you would want to shift our pattern register to get ready to start rendering the next pixel. And what would you do? You would do it when this is true in that case. And the same thing for all the other times you need to shift it on the screen. However, if you decide to put HPOS equals 1 instead of 0, or any odd number on the screen, what would happen is you would want to shift it to the left again after you rendered 2 pixels. Well, if you do it that way, we need to start in VDP column number 1 and render it there, and in column 2. And in column 2, the least significant bit of the VDP column number would be 0. So you can't use this simplistic thing, right? So what we do is we say, just remember where you start in terms of whether it's an even or an odd column. And if the current column is not even or the opposite of that, that is the point in time where you want to actually shift this thing. Okay, if you don't do it right, what happens is that the sprite kind of moves in weird leapy ways, and it's squashed on one end and not on the other. It won't render right. Okay, so this is just a really simple little thing, but I overlooked it when I first wrote it, and then I saw, oh yeah, we got to do this. Okay, so all this does is make sure that we shift this register after the second pixel that's been rendered from our sprite pattern. Okay, so this is like the only real trick in the whole design there. Okay, so there's the whole ball game. And with that, I hope to bejesus we're done with this thing. Unless there's some bugs that somebody finds. Now, I've gone through and I've grabbed some of the signals in the test bench here. I guess I should show you how I ran the test bench here. So in this directory here, the Nouveau VDP 99, if you type make this thing like that, right? So if I type make this, hit enter, it takes a while. Look at all the data in there. And then it will pop up this screen. And what I've done is I've taken a little, several minutes to go through and choose what we want to see. And what I've chosen are, all the bits from here. And then I've gone through and deleted a bunch of stuff that I don't care about so that we can kind of try and fit it on the screen. As you can see, it's a bit cramped. Then I went over to this sprite here, which is the 0th sprite. And remember, I told you I'd show you this. When you have that loop that generates 4 sprites, the identity of that loop was inst, and inside there I created these S objects that are type sprite. So when you get the waveform rendering from the test bench, this is what the tree will look like. As I said before, it will be recognizable. You can see instance 0, 1, 2, 3. These are your 4 sprites of type sprite, and those are the instance names of each one of them. They're all going to be called S. You get this weird thing because you don't want a name clash. So you need to have the array. That's why we named that loop inst. And we'll take a quick look at that to remind everybody in case you forgot. That is where? That is in here. Those are the names you see here. And this thing here that it's always annoyed me that I actually have to name this, but you know, that's why I need context, because these aren't really named. So what this does is it creates an array of 4 elements, because that's how this loop is set up. And each of the things inside there is going to be called an S, just like that, all right? So I mentioned that in the last video. So we got a little bit of closure there. Okay, anyway, that's where all these values came from. I grabbed some value out of here so we can look and see at what's happening in the 0th, the frontmost sprite that we find when we do the SAT table scan, okay? Okay, so there's a lot to look at in here. Let's make sure that we get our bearings. So for the most part, this top stuff up here, till we get to this blank line, is the stuff from the state machine. The stuff down here is the stuff from sprite number 0. All right, so what do I do here? We've seen this before when we're looking at our graphic stuff. So let me zoom way out so we can get, recognize this. You might recognize this, right? So this is a whole frame followed by the time it takes to do the vertical sync. So there should be a V-sync. Here's where the border goes blank during the V-sync. Did I delete the V-sync? It may be a signal we don't really need for this conversation. Is that it right there? That's the last row. H-sync. I may have deleted it to save space. Oh, there it is. There's the V-sync right there, okay? So that sort of makes sense because that's where our border is blank, right? Okay, and we don't really care about V-sync with respect to sprites, so I don't, that doesn't matter. That's just superfluous stuff. Now I'm going to zoom in over here, and we're going to look at 2 different areas, maybe a little more, of this screen while we play around here. Now, what we're looking at is the time before the H-sync, okay, for the very first topmost line on the screen that is active. All right, if we zoom out a little more, remember these over here are borders. This signal right here is the border active, okay? And you can see it's active an entire line. So everything over here is the top border being rendered. Then, when we get to the actual part of the screen with the active display, the first line that you could see, you got a border on the left and a right, and then a hole in the middle with respect to the border where all the video, the active display pixels show up. talked about that at great length. We talked about the graphics state machine before. All right. So what do we got here? Here's your sprite tick out that comes from the VGA sync module, which is the thing that says I'm on the what that really is. I said it in VGA sync. We saw that last time. Right before I start rendering the right-hand border. Now, this first one is kind of out in the middle of nowhere because nothing came before it in terms of the actual active display. So if we scroll to the right a little bit over here, we can see the next sprite tick out right there. And it's more obvious that that happens as we enter into the right border on the normal case. And this noise here, we'll see, is the sprite scan taking place. All right, so the first time we set that tick to go off where it would be, even though we're above that first line. And remember what I said before, when we're loading and we're scanning the SAT table, we are logically rendering the row number prior to the row, which is right here, that has all the visible stuff in it. So the row number, which is right here, this 2F, is our row number minus 1 of where this data will ultimately appear when we're rendering row number 30 in hex. All right, just to make sure that we all remember these things. So let's see what happens when we scan this SAT. Okay. All right, what do we got? We have, there's the thing that happens right before we'd normally enter in the right border. And we can see what's happening here. It's reading from the SAT table. These values here, I'm not going to beat this too much. They come from the configuration of all these values. Here's the sprite attribute base and the pattern base and stuff like that. And remember, these values are taken and then merged in with other bits to come up with the actual VRAM address. So the DMA address here represents the address of the beginning of the sprite attribute table. And remember, I don't, send these values in with a bunch of zeros after them. I send them in the actual bit pattern from that register. So this thing gets shifted left a few bits is the point. 1A is really this 0D00 for the beginning address. I convert this 7-bit value to a 13-bit value by shifting it over. All right. So what happens is I take that and I come up with the first DMA address. This is all the walkthrough we did in the last video when we're wandering through the scan state machine. And it, remember, has to read each one of the 32 table entries looking for the first 4 visible and then potentially the 5th that could be visible sprite. So what I have here, you can tell by the pattern, it finds in this SAT table the first one sprite entry is visible. This is probably checking the second one and finding that it too is visible. Then when we get to the third one through the 32nd, all these are not on the current line. I should not have said visible. They are potentially visible because they could still be entirely transparent on a given row, okay? So the first 2 sprites have a vertical position that includes the current line, is my point. None of the rest do. So let's zoom back in a little bit here. What do we got? And if we wanted to look around at some of the other values like the delta and all that stuff that we talked about last time, you can find that in the, the sprite state machine. Remember, I grabbed the signals from the FSM module here that we're looking at. We can add some more from here. I'll just throw on the delta so that we can see what happens when it's calculated. These are in alphabetical order. What do we do? Border collision. Is that right? Did I get the right one? Last pixel. Or is it like sprite delta? There it is. It's sprite delta. So you'll have a number in here. Let me put it up here so we can kind of see them together. See how it's 0? this must mean, and we can look at the test data that I used for this run. I'll show you where that is in a minute. It must mean that this sprite is set to run starting on the first visible line, which remember is FF for the row number. In fact, you can see on VRAM D out, it is FF, because remember the first visible row is -1. So it goes through all the malarkey in the SAT scan state machine and comes up with 0 for the actual thing, or the distance, remember. This is the distance to the current row. It's on the current row, so therefore it's visible, and our state machine wanders through. As you remember last time, it needs to read what? This is going to be the horizontal, and like the pattern and the color and stuff like that. So it's reading the other entries from the sprite attribute table here. There's 4 total bytes that it has to read for one SAT entry. Now we skip this one here, as I talked about in the state machine, because it takes time to look things up in the memory. We don't yet know what's going to come after this, so I can't load the pipeline. I can only do one at this point in time, so I have to waste this time period and not accomplish anything because I don't yet know if I need what to do next. Once I get the value, I say, okay, let's read in the other 3 bytes. Now I also have to read in the pattern value as well when we look that up in the pattern table, okay? Now, at the end of this whole thing, we need to move on to read the next sprite attribute table entry. And you can see I'm at D04. So the first one is at D00. The next one's at D04. The one after this will be at D08 because each one of them are 4 bytes long. And C and 10, 14, 18, 1C, and then 20 and so on. All right. So you can clearly see the sprite table being scanned here. All right. So what do we got? The first 2 are in covering the current row being rendered, and you can see that the delta being 0 in both of these. You can also see the FFs here, meaning that these 2 sprites actually are butted up against that top row. In other words, they didn't start up in the border and then start rendering down here in the bottom half. These are positioned to start in the first visible row. When we read the next sprite, what are we doing here? We see we got an 01 right there. The distance is FE away. That means that, obviously it needs to start below by 2 pixels from the row that we're on. And the next one has got an 02 and an 03 and an 04 and so on. And this, when interpreted as an unsigned binary value, means it's really far away. In other words, it can't possibly appear on the current line because this distance is too far. It has to be within 8 or 16 or 32 pixels, depending on the magnification and the size settings. We talked about all that fun stuff last time, too. So you can clearly see it scanning through here, and you see this gap at the beginning of each one of the sprites. You also see a gap over here that occurs at the end of each one of the sprites that are actually visible, all right? Now, it's important that we don't keep interacting with the VRAM too often. If you look down here, we talked about this last time, the VMA read tick signal. Here's the one that actually goes to the VRAM. Let me put that down here. What we have is the read tick from the graphics, read tick from the sprite, and last time I showed you I kind of OR those together. If either one of them is going to be needed, it sends that to the actual VDP VRAM, okay? And the VRAM responds based on the address. The address is calculated up here. There's the actual address, the one from the graphics engine currently not running, one from the sprite. So these kind of paired up and go together, and now I got them out of order. There we go. So there's graphics sprite, and then the chosen one using the priority encoder we talked about last time. And the same thing here. So about these gaps of unused space, as I explained, we can't know what to do when we're trying to read the vertical position of the next SAT entry. Now, it's critical that this not stay true very long in a continuous fashion. It has to have holes in it. As I explained at great length long before, that the CPU needs to be able to access the VRAM from time to time. So where are we at here? We are, okay, so we just went over, here's the scan, here's you find out what's going on in your bearings if you want to look closely at what's going on. When we're done scanning, here's the active portion of the screen, because here's the left border, as I said before. Now, the left border, this little tick right there, is probably the signal. I believe that is the signal that we sent into our sprite. We scroll down here, and what we're looking at are all the stuff that is from this guy right here, which is the frontmost sprite, and we should see it getting loaded right there. This must be the load tick during the sprite scan at the end of the first sprite scan here, right? So what are we doing here? Here's the first sprite scan, blah, 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 blah. It gets its values, it gets all ready to go, and it starts the next one going. And at the end of the reading of all the data for the first sprite, this tick goes through here. And it goes through here because, remember, if we look at our code, it's probably the last thing we do before we start reading the next sprite data. And we set, the next load text signal should go true in the next period, which turns out to coincide with the period where we read in the first value for the next SAT entry. So this is where our sprite gets all of its data from. And you can see these things getting filled in as they're being read from the SAT, the 3 and the 20, which the horizontal position here, and the 3 is the color. Okay, what else do we got? Foreground color reg, which gets loaded into our sprite here. Okay, so all the stuff that the sprite gets loaded with happens at the end of this sprite tick here, because this is when it's true on the next rising edge, which is why 20 gets loaded into the HPOS, even though the state machine had it earlier. And the 3 for the color gets loaded in here as well. The other things like the phase and pattern down here, you can see that getting loaded in as well. The mag is 0, so it didn't change state. And what else is on here? The reset. Remember when I said at the beginning of the sprite table scan, we reset all the sprites to make them transparent. So this is the galactic reset. All sprites get reset during this time period, and that's why active goes off. Active goes on when we get to the point where we're starting to render sprites, and it gets shut off at the next reset. So that happens there. Here's where we are fully loaded, and we could go active and run here, but that doesn't happen until we get the go signal, right, at the beginning of the left border, which will happen over here. He goes active right there as a result of this, which is our col 0 tick, which, as I said, is the not so wonderfully named variable that represents, here's the beginning of the first column where the sprite could become visible from the context of the sprite object itself. And you can see something starts squabbling over here. That's probably our counter. Yeah. So HPOS reg starts counting down as soon as we get this signal here, because if we scroll up, we'll be in the border at that time. All right. You can see it's derived from this last call out, obviously, as what we use to connect whoa, wrong screen there. Which is what we use to generate this signal here in the sprite FSM file, okay? So what happens? After that point in time, we say it's active. We start counting. When we get down to 0, you can actually start seeing that the color out from that sprite starts squabbling over here, and it could have as many as 16 opaque pixels rendered at that time. The pattern that comes out down here is it shifting, all right? And as it shifts, it takes the most significant bit of the thing, and it runs it through its, the foreground counter. So this will either be 0, which is transparent, or it'll be the FG color. The FG color is 4. So if we zoom in right there, it should go back and forth between 0 and 4, which it's going 0 to 3. What is up with that? Foreground, read. Be careful. FG color reg is the value that we latched into our sprite during the configuration. This 4 is the input on the port to the sprite, which is left set to whatever garbage is sitting there after the end of the scan. As you can see, the foreground color goes 0, and then it probably is a 3 there. Then it changes to 4 because that 4 is probably the foreground color of the second sprite. So it's critical that we look at the right trace. Question everything is always what I do when I'm playing around with stuff like this and kind of spot checking. Yes, 3 makes sense because I had the wrong line highlighted here. 3 is the latched on configured value for our current sprite. You see HPOS reg counts down. It obviously hits 0 at that point. And once it gets to 0, that's when we start seeing the color out. It's also when we start shifting our pattern register. So we take the first most significant bit, 8100 for the pattern, that's on. That's why we got a 3 there. Then there's 3 zeros and then another 3. There should be 6 zeros. 6 pixels of transparency in here, right? Then a 1 means there's another single pixel over here and then nothing. So this looks like it's right, okay? And it's rendering this sprite on top of the active display region here. We already talked about, fetching in all this graphic stuff and the patterns and it shifting out over there and the DRAM out. Somewhere in here will be the graphics out. Here it is, color out graphics, color out sprite. So the sprite output, notice we've got more coming out than we have down here. That's actually because we have 2 sprites on that top line, as you remember. So what we're seeing, so here's the second one's being right here. One of them's got a foreground color of 3, the other one's got a foreground color of 4. Good thing I didn't make them the same. That'd be real confusing. So there's the 3 and the 3 we just looked at. We scroll back up. So we have, our regular text here, our graphics pixels, right? Which must have a foreground color of 7. So let's zoom in here. What do we got? We would want to see an opaque pixel whose color is 7, but there's a sprite pixel here for 3. For the first sprite. Here's the second sprite, who's the 4. Then the sprite becomes transparent. And you can clearly see that on the color out, which is a composite of the graphics color and all the sprite colors, that we end up with this. So we end up with these. The priority encoder said, I want sprite 0 before I want to see sprite 1, before I want to see, so on, all the other sprites before I want to see the color from the active display graphics region. So right now the sprites aren't covering each other. We don't have a collision. So they're interleaving, sprite, and then the graphic color there. Same thing over here. As we scroll across the screen here, we should actually see, in this test case, a collision take place eventually on one of these. In fact, these should collide. I think I have a test case where I did that. Where's the collision? Zoom way out here. Is this it here? Yeah, it is. There's your collision. There's a cat in here meowing, but we're going to ignore that, right? So if you're allergic, don't sneeze. All right, so what do we got here? On the third row, apparently we've got a collision. And in that case, we should see the priority encoder choosing one sprite opaque color over the other. So let's zoom back in here and watch that take place. Of all the people in the world who view my videos, it seems the cat might be the only one who made it this far. Why are our family pets more interested in what you're doing than anything else on earth? Don't you have some mice to go catch in the backyard or something? All right, moving on. Here's the graphics color is a 7. The sprite is a 3. And I suspect that if the collision went on at this point, here's the collision. What would happen here is we have at least 2 sprites. Below here, we would see that it would have different colors coming from the sprite state machines. So this one is a 3 from sprite 0, remember. So I go down here and I say insert a blank line so I can keep these in groups. And I go to this second sprite over here, which must be the one I assume it's colliding with. And I just say take all these signals, because I have an infinite number of pixels on my screen, of course, right? So these, turn that off. What do we got here? So here's the second sprite. Foreground color is 4. And he is active right here. And we know that sprite 0 is also active at the same time. So what would happen is that the encoder in the state machine up here should have chosen 3 as it's in front of 4. If we go on and look at the other sprites at this point, we're on, what line number are we on? We're in here a ways. I don't know how many sprites are active right now. We got to scroll up and then look at what. We want to watch this fetching going on over here. We can watch them fetch. I see only 2 here. You should also see the sprite counter counting, 0, 1, 2, 3. Where is that? Did I keep that on the screen? Sprite tick. Oh, I'll bet it's down there. Sprite counter, there it is. Counter reg is the thing we want to see. There you go. 0, 1, 2. It's showing it in binary for whatever reason. Let's go over to hex. All right, so we got 0, 1 that gets used, and sprite number 2 here means it never found 1 for the third sprite. And we can kind of like scroll over the screen now. Notice it goes up to a 3 here. So here's a line of video that's got 3 sprites on it, 4 sprites. Eventually we should see 5 sprites, I think, because I wanted to test the 5th sprite. Wow, I didn't do that. Oh, it doesn't go to 5. It stops at 4. Here it is, right there. I'll bet that's the 5th flag. There you go. Let's look at it finding a 5th sprite. Remember how this thing works. 0 is the first one. 1, 2, and 3 are the other 3 of the 4 visible sprites. This thing stays at 4 during the scan, and the scan will stop if the counter is 4 and I run into a visible sprite. So if we look at this from a distance, we can see that the sprite scan took this long. All right? And then over here, the sprite scan took a lot longer when it never found a 5th sprite. So this is it scanning all 32 and finding 4. Here is it's scanning less in finding a 5th sprite earlier. Okay, so we can go ahead and zoom in here. And now you can see what's going on. It found 1, it found 1, it found 1. 1, 2, 3, 4 good ones. And then when it gets to the very next sprite, it says it's visible, and therefore I have too many, so I bail out. We talked about that when we looked at the state machine, and it remembers that it has a 5th sprite, and the sprite number is given by the counter that I just brought up in here, right? The sprite number 4. Therefore, you can see it in the register there. We set the flag for the status register right there, and it goes on and stays on just like the collision flag does, which went true over here, right? And they both stay on until the status register is ultimately read. And in the simulation, the status register gets read way over here, as if it got read because of the frame status flag, which I think you see right there. That's the IRQ. Oh, there's the reset glitch. That's what happens there. That's the single tick that says the CPU has read the status register. Okay, so that works as well. What I don't see on here is the IRQ output, and that's probably because the IRQ output doesn't come from the state machine per se. You'd see it way up in here. Here's the IRQ, and you can see that thing goes through here when you get to the bottom of the screen there after it renders the last pixel. We talk about that in the state machine. So in the simulation, the CPU effectively reads the status register. It waits a little while and then reacts to that interrupt there. And you can see, whoops, the status register is getting reset there. So this thing seems to work okay. And even better than going through all these timing diagrams, we can actually key up an application and move around some sprites on the screen and watch it all work, which is far more fun, I admit. So those of you that have suffered through this long, let's have a look-see. Now, lucky for me, one of the guys that hangs around in the Discord wrote this test program. SP2, I called it. If you run this program, it'll generate a screen and let you move around sprites with the joystick so we can watch what happens when we have 5 on a line and stuff like that. You hit this button here and it cycles through which sprite you want to deal with. So you can see the collision down here going on, all right, and off when we put them over it. So let's put them all on one line. All right, so you see the 5th sprite go active here, that number 4. It would be nice if you said 0, 1, 2, 3, 4, but okay, so it turns out this is sprite 0, 1, 2, 3, and 4 for that 5th one over there. So that works. And S, I don't know what S is supposed to mean. That is true for the 5th sprite, and I don't know what the other one over there is. You can also see that even, if the 5th one, it comes before the rest, it's still the one furthest down in the layers, right? So it is the 5th one no matter where it occurs. It's not just the 5th one to the right, it's which one in the SAT table, right? And you can see the XY positions on here as you move it around, the magnification, the ECB, and I don't remember how to do that. I should probably hit like an M on the keyboard. So now they're magnified, and of course we have collisions because they're all overlapping now, right? So that's pretty cool. And for the currently selected sprite, if I hit E, you can see the early clock going on, okay? So that early clock is off, early clock is on now, okay? You can see the ECB there, right? So if I move this thing to the left, what will happen is it can go off the left side of the screen and be hidden behind this left border. Remember, it goes active here, so it's actually being rendered. You don't see it because a higher level in the module stack is painting the border on it in front of the sprites. And if I keep going to the left, it appears way over on the right there. Notice I can't move it over here. It can't go there. Because remember, the early clock says I can only render it over here. And because, as I explained before, there's only I can only express 256 for the origin of the left edge. So if I allow it to go all the way over here, then this much of the screen can't be used over there. So that's why they have that early clock jazz on there. So if I actually move it way over here, the joystick here, and leave it there, and then hit E to turn off the early clock, you see it's all 32 pixels to the right and hiding over there. And the furthest it can go is here. I cannot make it disappear entirely there because, as I explained before, the 256 is really 0 through 255. And that is always going to be visible if the far left edge of the sprite has opaque pixels in it. If I go one more pixel over, if I can do that really quick with a joystick, I went more than one, it'll turn out to be butted up against the left side of the screen. It's going to be hard to get it to go over there. Let's see. Oh, there we go. I got it there. See that? Now it's just right over there kissing the left edge of the screen. If I go up to the top, it goes off vertically. That works good. Goes down vertically. If I keep going, it'll just go around and around and around. Same with this, because it just keeps adding one, and when the carry bit overflows, it goes back to 0 and comes back to here, all right? So that's pretty cool. And if we magnify, it should still work because this is 8 pixels wide. 16 can still fit in here. And these are obviously 16-bit wide pixel sprites anyway, because you can see visually how big they are. In terms of pixels, you can count them all out. There's at least 4
5 right there, 6, 7, 8, and then another 8. So even when they're not magnified, you can see that they're 16 pixels wide. So this is 32 total. And with early clock off, you get that. Early clock on, you see it leaps to the left. I should be able to get it completely hidden in there. Oops. If I can get the joystick just right. Should maybe have a modification put in the program where we can move it 1 pixel at a time, maybe with the keys. Of course, I could look at the source code. Maybe he does have a way to do that. I don't know. Come on. This is like a game in itself. Can I click 1 pixel? I can't do it! There could actually be a bug if that is in fact the case. You can even see a gap there. The problem is how do you click the joystick and just move only 1 pixel? It's making pretty big leaps here. Oh man. It's probably the luck of the draw to just get it to the... Oh, come on! Well, you can clearly see X is set to 3 there. Now it's, wow, 64K. Hello. This is funny. That's a wraparound in his counter. He's using a 16-bit counter to then throw away the left half and keep the rightmost 8 bits. That's funny. Dave, we have a bug. Oh, come on. Can I get it set to 0? I can't seem to... Oh, I had it. Oh! 0. Whoa! I think we have a bug. I can see it and it's set to 0. The plot thickens. Either he's printing it wrong or I'm rendering it wrong.